kind of what the first main point in the proof is this cumulant expansion. So have this
刚刚脑袋是全屏，这里有点反光。
Okay, yeah.
okay. So let's say Z1 to ZS is a sum okay. So this is the tensor part, factorized part. And this is equivalent. Okay, and then we have this expansion. So it's L tau, or let's say, so L tau sum over the collision history diagram. And let's call this collision history diagram, let's call it M. Okay, so let's call it M. So there is IM. Well, this is so let's say node M is a collision history diagram. The one we draw, last time, that involving the particles Cj or Jh. Okay, so contains multi-layer. And then this IM, we'll see in more detail today, is integral expression associated with M. And what it represents, remember that this EH is a cumulant, which is a part of the joint density. So you can think of EH as a quantity that has the same kind of a feature as same quality as qualitative the joint density. And then so this IM is also so represents basically the joint density of particles in H. Sorry, particles in H. Of course, assuming under the assumption, because we are already having this expansion with the collision history diagram, with the diagram M, also under the assumption that all collisions in M indeed happen. Okay, so the reason I'm saying this is because if this IM, is a probability density, then later on we measure the L1 norm in IM because we are measuring, and remember from last time we're measuring the L1 norm of this EH, and then we're measuring also L1 norm of this IM. If you measure L1 norm, we are exactly reduced to the probability. The integral of the probability density is just the probability. Okay, so this is a thing, and then later on the quantity we're going to estimate is precisely the we'll estimate this is this, let's say Xiao 1, which is less than sum in M L1. Okay, and then this quantity just means probability that all the collisions M indeed happen. Okay, so this is our setting from last time. And finally, let's remark that we are assume the truncation that the total number of particles in M, or particles involving M, is less than the power of log, let's use epsilon, to C. And then for each layer, each cluster, the number of recollisions is less than an absolute constant. So reason for this truncation, first truncation we already explained last time. The second truncation is basically because because we want to avoid the scenario where we have a small number of particles which keep colliding, for many times. Let's say this. We need this to avoid kind of the scenario that let's just say 3 particles, or kind of finite many particles, let's say, or 1 particles colliding many times. Okay, and this scenario, it is known that if we have scenario, then we cannot gain kind of enough power that is as much as the number of recollisions. There are so many recollisions, but you cannot gain too many power. So this is why we need to introduce this truncation. Okay, so let's summarize what we have so far. So we have this interaction diagrams M, which we'll draw immediately. And then we're having this expression IM, which will explain what it means. And then our goal is to prove that, we have these upper bounds on L1 norm of IM. And remember from last time, we have this bound should depend on 2 quantities. Let the total number of particles in M be X, total number of recollisions M be rho. The goal is prove that this is less than, okay, tau to the X times epsilon to the alpha rho for some constant, positive constant alpha. And once you have this, this will be enough to cover, to cancel, the combinatorial factor from the summation, the number of choices for M, and then matching with this, you're going to get the good estimate for the total L1 norm of the cumulant. Okay. So this is the recap. And now, so let me first explain that this factor tau to X is not hard to get. So, so how do we get how do we get tau to X? Well, this is easy because each collision, because once you fix the collision diagram, then you are fixing the the position of each collision, who and who collides, and when do where do they? So I mean relatively the ordering and everything like this. So each collision, so there are x total particles, and they're essentially x collisions. Now each collision belongs to a fixed layer, which means that it has the layer has length tau. So the time, it has a kind of a time window of collision of length tau. If we integrate in time, we get tau. But then since we are integrating in all the x collisions, we're getting tau to x. So this is a kind of a easy argument that allows you to get this factor tau to x from the L1 norm, which is a probability. But the hard part, of course, is to get this power, epsilon alpha rho. And we'll see, let's start with a simple example, and we'll see kind of in general, like how to get it. Of course, this is the main part of our proof. Okay, so maybe a simple example is when, let's say, when we have three particles, we have two collisions, that's when you have no recollision, but when you have three collisions, you're going to have one recollision. And how are you getting this extra power from this from these recollisions? So the toy. So three particles, let's say A, B, C, two collisions. So if you have two collisions, let's say A collides with B, then B collides with C. Okay, let's say you have this. Then how to do it? You consider you're talking about probability, right? Probability, so given A, let's say the initial place and velocity of A can be given arbitrarily, but then once you get B, the probability that the B collides with A, well, you can see, remember A is A is epsilon kind of ball, and it travels at time interval tau, and this is tau, and this is epsilon. Okay, so the volume of the whole thing is like epsilon 2 times tau, which is volume. The probability that the B collides with A, of course, is equals to the so epsilon. Let's say in d dimensions, that will be epsilon d minus 1. The probability that B collides with A is the number of particles in this range, which is n times epsilon d minus 1 tau, which is equal to tau. Okay, so see here we get this tau. We get this tau factor, which is on right hand side. And remember that this collision is fixed in the time layer, so we only have this time tau, which is the length of time layer. Okay, so let's say given A, we want to choose a particle B that collides with A, and then we get this probability. And then given A and B, the probability that C collides with B is equal to, again, if you fix the parameters of B, again we have n times epsilon d minus 1 tau, which is also equal to tau. So then we get a total, the L1, which is the total probability, which is equal to tau square. Okay, so this is the simple case where I have no recollisions. So we have no recollisions. Okay, so now if you have three collisions, so let's say now if you have A collides with B, B collides with C, and then A collides with C. So what this means is that given A, the probability of B colliding with A is equal to tau. So this we know. And given B, the probability, let's still say given A and B, probability of C colliding with B is equal to tau. But then we have this third collision here, which means that C not only has to collide with B, but after colliding with B, C also must collide with A. Remember that the position, the parameters of A is now also fixed. The probability of C colliding with B and next colliding with A will be something less than tau. So actually will be something tau times epsilon alpha for some positive alpha. Because you have one more collision which will get you an even smaller probability. Okay, and then you get is less than tau square times epsilon to alpha. Okay, so this is what happens, in the case of the simplest case of three particles and no recollision or one recollision. So our goal is to extend this picture to general diagrams. So now we can have basic arbitrary diagram. Of course, those diagrams that do naturally occur in our cumulant expansion, we'll specify them later. But this diagram can be arbitrarily large, and structure can be arbitrarily complicated. So our goal is to show that even in these arbitrarily complicated graphs, we still can get this factor here, which is even proportional to number of recollisions. Okay, so this is what we'll do for the rest of today. Before this, let's just review the notions of collision history diagrams, which are also called molecules. They are essentially the same thing, just express, describing different aspects. And then what is this IM? It's a probability, the probability of all these collisions happening, but how can we write it as an integral, and how can we manipulate this integral? Okay, so let's just start by saying here the collision history diagrams, we also call it molecule. So actually, let's move it here. So we have these are the particles in H. Okay, these are the root particles that we defined last time, corresponding to the last layer. And these particles are going to have, connected by collisions. So what you have here, then you are going to have these, okay, so let's say you have these things, and you have these things across the layers. And this one the same. So let's say you have, okay, so let's say you have this. So this is okay, so let's call it, this is L tau. Okay, so this is L minus 1 tau. Okay, and these blue ones, we keep going. And we think of, we may have these conditions, and maybe, for example, these conditions, and then they are kind of put together, and then we are having something being the green, and then we're having these other things, whatever, pink, and then same thing here. You may have collisions that go like this and go like this, and this, of course, is also part of that. It has no this part has no collisions in this in this layer, but then it just directly kind of directly go through so directly go through here. Okay, and so on. So, and then in the end you get back to 0. Okay, and so this diagram, and so basically the kind of the feature diagram we also described last time, the fact that you are dealing with accumulants means that any two of the particles you have in H, any two of the root particles, I mean, so any one of the root particles, and the same when any one of the particles that occur in the previous cumulant expansion, like the any one of the blue ones. So let me kind of circle it here. Any one of the red ones, any one of the blue ones, any one of the pink ones, and so on. So feature any particle of color other than green here, of course, green means that you are not so green is a special color, means that you are factorized at this level, and you are not going to occur in the previous cumulant expansion. Okay, so remember this green here at this level, and this green occurs at this level. So for any particle of any color other than green, it must be connected to another particle of the same color. Remember, of the same color means that the blue particles, for example, blue particles means that these occur in the cumulant expansion at the time L minus 1 tau. And the red particles just means that they occur, in the cumulant expansion at time L tau, and so on. And the pink is here. The same color. In the, in history. In history means that kind of, let's say backwards in time. Backwards in time. Remember, we also said that these feature means that these particles are connected back in time, but they're also connected forward in time, which means that you're creating recollisions kind of for each set of these particles. For each for the set of red particles, you create many recollisions whose number is comparable to a number of red particles. And then for the green particles, independently, you create recollisions whose number is again proportional to the number of green particles, and so on. Okay. So this is the first thing, the structure of the diagram. And the next Next is the probability integral IM, which is a okay, so let's say the L1 of IM. Probability of all the collisions in M indeed happen. So how do we represent this as an integral? So let's copy this diagram here, and we'll see. So to estimate the probability, it's given as an integral, but then how do we, this integral involves many variables. So one choice of the variable is for example, you you set them as all the the kind of the final like the final states of the all the particles. So for example, you have these red particles whose final state is whatever they have at time L tau. But then there are also other particles, the particles that goes this way. This is not a red. It's not the root particles, but it's something that's introduced in the collision in layer L. And you have these particles which are kind of introduced in the collisions in layer L minus one and so on. But no matter what we do, you see there is always a complicated change of variables or substitutions involved in the integral because even if you just focus on the red particle, so let's say this is the red particle we are looking at, and then it's it may be you may trace it back all the way to time zero, and then you get some particle down here. Okay, and this particle coincides with the top red particle, but then you see the velocity, the position velocity of the particle of this particle at time zero, represented by this purple kind of vector, will be completely different from the position velocity of the red line, representing the the particle at time L tau. In the whole process, there is a many potentially many number of collisions that may happen to this particle, and this particle, the velocity of the particle will go through extremely complicated change of variables. And we don't want to kind of incorporate these change of variables in our integral because that will be too hard, too difficult to handle. So the way we do it is that we want to enlarge the set of variables we integrate, and we include all the the states, the velocities of all the intermediate positions, all the intermediate stages of particles. So let's say, so if you have so we express let's say probability, let's call it the probability of M as is integral over all variables. So let's call it over the variables that represent intermediate states of all particles. Okay, so this is another key thing now you do in our proof. So let me demonstrate it by one example. So let's say we're in a case where we have 3 particles and 3 collisions. See the 3 collisions. Okay. So how do we represent this by a diagram? Well, this is easy. So what we have is we have 2 particles. Let's give it different uh different colors. Okay, so this is so this is A and this is B. Okay, so okay, and then let's say B collides with C. So there is a third particle that collides with C. So let's say there is a C here. Okay, so let's say C, where does C go? C could go this way. So let's call it C. Okay. Uh, let's draw it kind of more carefully so that it can collide. Okay, so let's say it's like this. And then B collides with C, and then C collides with A. So C collides with A. So if we draw it C, and this is A. And of course, this is B. Okay, so this is the simplest case of three particles and three collisions. So here we want to, define the variables, that kind of completely determine this collision diagram. So let's say we can choose it. There is, let's say we have this Z1, Z2, Z3. Okay, so this is 100 is a incoming initial kind of position velocities of the particles A, B, C. Fine. If we know Z1, Z2, Z3, then this completely determines the other variables. So these ones are the free variable that can be chosen kind of freely. And then once these are fixed, then all the remaining kind of variables are fixed, because if Z1, Z2 fixed, then you have unique collision that determines the velocities of this, velocity of this, and then this is fixed, Z3 is fixed, then this uniquely determines the velocities of this and this, and finally this determines the velocities of this and this. Okay. Another choice is you can choose, for example, the kind of the final velocities of ABC, which is Z4, Z5, Z6. And again, if you know Z4, Z5, Z6, then you can backtrack and calculate all the subsequent velocities. And Z4, Z5, Z6, they are again free variables. But as I just explained, we are actually not doing this. What we are doing is we are including not only these Z1 to Z6, these um, initial and final velocity, we're including all the intermediate velocities. And this includes, for example, this guy Z7, Z8, Z9. These are intermediate velocities, and all the 9 variables, they are not independent. They're linked by a number of equations, but that's exactly why we introduce them, because we now we can talk about the integral in all these variables, but they are not independent, so we are simply introducing some delta functions. Okay, so the probability of M is an integral. Okay, so let me say, in addition to the to the vector integrals, we also have the time variables. Remember that there is a collision here that happens at a time. Let's say we have T1. Let's use a different color. So T1, T2, T3. Okay, so we have this delta, which we'll see, like they represent a huge product of delta functions, and then we have um, dz1, dz9, dt1, dt2, dt3. So this is our idea of representing this probability, this whole probability of the of the whole thing as integral over all the intermediate velocity variables and over all time variables. Okay, so now what is this delta? This delta, first of all, you have your initial data, your input data, which is basically okay, so you have this, let's say f, 0, z1, f, and z2, it may be like f, some, Okay, so let's actually write it here. So f L1 tau z1, f L2 tau z2, z3. Remember that these are solutions of Boltzmann equations. These are solutions. So from our knowledge of Boltzmann equation, from our assumption, we know that they are not only factorized, but they are very nice, nice and fast decaying functions. So we don't need to worry about those. And then we have these delta functions. So delta functions represents dependence, interdependence of all these different ZJs, and this interdependence is given by the collisions. So since we're having three collisions, so we have this delta function is grouped into three groups. So there is a delta of the first collision T1, and what is this? So let me write it as T1, and then we have the velocity Z1, Z2, Z7, Z8. Times another delta at collision T2, we're having the four velocities Z8, Z3, Z9, Z5. And finally, at the collision T3, we're having Z7, Z9, Z4, Z6. Okay. Now, what is this delta? You can write it. Basically, it represents a delta function that represents relations of the position and velocity of the particles before and after the collision. So let me write this one, and the others are the same. So let's write delta of T1, Z1, Z2, Z7, Z8 equals the first delta function of Z1 plus X1 plus T1 V1 minus X7 plus T1 V7 times a function of X2 plus T1 V2 minus X8 plus T1 V8 and it times the delta function of okay, so it will be V7 minus V7 V1 minus V2 dot omega V8 plus, sorry, I think we have V, and here we have a V8 minus finally you have a delta of X1 plus T1 V1 minus X2 plus T1 V2. Okay, so let me explain what this is. Okay, so first of all, this quantity, because when we define the ZJ, so ZJ equals XJ VJ. Okay, now VJ is clear. VJ is the velocity of the particles in this period. Remember that each kind of node, each what you call atom, each atom represents a collision, and each edge, each segment represents the portion of a particle between two collisions. Now, if we have a particle between two collisions, then in this time, their velocity is going to be constant on this time. So, so then we have uniquely defined the VJ. Okay, unique define the variable, time variable VJ. sorry, vector variable, velocity variable Vj. Okay. And then what is this xj? Because again, in this time, the particle is linearly transport. So then the kind of the position, the trajectory of the particle is represented by a single line. So we can represent this trajectory by a single variable xj, which is the position of the particle along the linear, linear kind of movement, linear trajectory, then transported backwards to 0. And this is actually. The reason we define it this way is because we want the x-ray to be uniquely defined, and it's not that we define this actually associated at this time or associated at this time. We want them to be the same. And in this way, this quantity x1 plus t1 v1 is the actual physical position of the particle at the collision time t1. Okay, and then this x7 plus t1 v7 is also the trajectory of the same particle, at this collision time t1. And then the cell function just represents that this particle is moving continuously. That the position it has, at t1 following this trajectory is equals the position of this particle at time t1 following the next trajectory. So this is just continuity equation. Okay, so this continuity equation and the same this continuity equation. And these two are are simply the velocity, the collision formula, the formula of how the velocity changes after each collision, and omega is the is a vector connecting the center of the particles, and this one is the condition. So this is the continuity equation, and this one is the collision formula, and this one is the distance between the two particles at the time of collision is equal to epsilon, and this is exactly the collision condition. And of course, omega here is precisely 1 over epsilon times this vector. So this belongs to unit sphere. Okay, so this is a complicated thing, but the good thing is that these quantities, especially these delta quantities, they are defined kind of only locally. Okay, so because this quantity only depends on these few variables z1, z2, z7, za that is directly linked to this particular collision. Okay, it doesn't depend on anything else apart from these four variables. And in fact, each of the factors we define in this delta function only depends kind of on the local variables around that particular collision and around that particular atom or vector, such that we don't have these long chains of iterated change of variables, which is something we want to avoid. Okay, so this way we obtain this integral expression. So let me write it here in general. We're having this probability m is the integral over all vectors, all time variables, that we draw, in this picture. So we'll get back to this picture. We'll re-examine this picture later when we discuss the algorithm. But okay, so then, and we have this delta, all collisions, delta of t n z1, z2, z3, z4. So this is the collision time, and these are the the vectors, the velocities, let's say, at the collision. Okay, and now our goal is to estimate this. How do we estimate this? How do we estimate this, and especially how do we get this epsilon to the alpha rho? Okay, so of course there should be a normalizing factor of n to the of this epsilon minus d minus 1, but we omit it. But essentially, this is the kind of thing that we're aiming at. Right, so maybe we maybe we can pause a little bit, have a little bit of break, like I don't know, 10 minutes, and then we can resume. Would that be good?
Uh, Hello, say it. Yeah.
Yeah, yeah.
Okay, okay, it's okay. Now you can continue.
Yeah, I mean, do you want to have a 10-minute break or
Yeah, 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 yeah. Okay, okay, okay. Yeah, 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 yeah. We can. Yeah, yeah. Thank you.
嗯，没了。
结束了。那没有结束，还有我们该休息10分钟。Okay, so maybe we can resume.
Yeah, okay.
Okay,
Yeah.
okay. So, uh, let's study, how to analyze this integral. So with this so many variables, so many, the delta functions. So again, let's examine this picture. And then let's say look at this integral here. So actually, let's move it down here. And we have this. So this one. So because these delta functions are the main thing, so say probability. Okay, so we have this product times d z1, d9, dt1, dt3. Okay, this is our integral. So how to do it? So let's say, since we are having this, the first factor here, t1, z1, z2, z7, z8. So let's first keep it aside. So we can write it. So this thing, to evaluate this integral, we can write it as integral delta. So let's copy this here. Let's copy this here. So okay, so okay, but these factor is going to associate with the variables dt1, d z1, z2, z7, z8. Okay, and then we have this times the next integral. Next integral is going to be involving this second factor. Okay, so we have delta t2, z8, z3, z9, z5. Now, what does these factor involve? What variable does these factor involve? We have t2, fine, dt2, but then we have z8. Z8 is already written down here, so don't have z8. but we have Z3. We have the Z9, the Z5. You see, we're having, in the first integral, we're having, 4 vector variables here. So actually, let's draw it. So this one, this one, this one, this one. Now here we only have 3, which correspond to, these 4. And here we have 3, but then we have one thing that is already written down in the previous line. Okay, and this is second factor. And the third factor is the same. We have only the third factor left. We have T3, Z7, Z9, sorry, Z7, Z9, Z4, Z6, and then we have DT3, DZ4, DZ6, and these are the correspond to here, and Z7, Z9 they already fixed in the previous integrals. Okay, so this way we are writing our big integral into an iterated integral, and in each step of this iterate, we're integrating in one time variable, you see, and this some number of vector variable that's associated with the one atom in this picture, which represents one collision. Okay, so and of course in the order of integration, we first integrate in T3, Z4, Z6, and then we integrate in T2 and Z3, Z9, Z5, and finally we integrate in T1 and Z1, Z2, Z7, Z8. Okay, so basically if so here like in this writing, we are first looking at the first delta factor, and we list associated variables there, and then we look at second vector right in the second line, and then we have this, and third delta function, and we write in third line. And each delta factor corresponds to exactly one, collision or one atom in this picture. Okay, so then the order we're choosing here precisely ordering of the atoms that we select. First look at this atom. This atom, let's call it maybe X. This is Y, this is Z. We first look at atom X, and then look at atom Y, and look at atom Z. Okay, so basically, in this way, basically we know that if we have any kind of a sequence of atoms that we're selecting, we can always write our integral as an iterated integral associated with this sequence of atoms, and this can be interpreted in our language called the cutting algorithm. Okay, so next let's talk about the cutting algorithm. So basically what we do at each time, choose an atom. Atom means a collision again, and cut it as fixed. Okay. So this means that if we choose an atom, so again, let's start with this picture. Let's say we draw it again. So we have two. Have this red, green, blue. So we have this. So this, so this, and then you have a. Okay, so let's say we first choose this one, the top one. So this is the first one we choose, and we cut it as fixed, means that we first of all cut it, turn this into okay, and we have these two things. We have also another red here. Okay, so imagine you have a pair of scissors that you cut your molecule, your diagram, along these two edges associated with this atom. Then you're going to turn it into these two pictures, and then we cut it as we cut it free. Sorry, we cannot cut it fixed. We cut it free. When cut is free, that means we are exactly setting these as a so-called free. Each of these edges, this edge and this edge, they are cut into one free, one fixed, and this is fixed. This is fixed. Okay, and what this has to do with integral, remember that the variables corresponding to this free. So we have variable z4, z6. Sorry. So actually, no. Okay. So sorry. So let me draw it again. So without definition, we're for cutting the left one for the left. Cutting the left one first. So let's redo it. This one. We have this. This. Okay. So cutting this one first. We're cutting this one first. And how do we cut it? Imagine we put a pair of scissors here, and we're getting this, and then we have then this is sorry, there is there is nothing. Yeah, this is correct. It's correct. This is there's a red, and this is free. This is free. And then we have two things here. We have this, we have this, and we have this, which is fixed. Then we have this, which is this is fixed. Okay, so again, you look at this this atom on the left on the left, and then you cut it along the two edges that is used to connect to others. And each edge that is cut, this red edge is turned into one free and one fixed. And the blue edge is the same. It's going to turn to this one free and one fixed. Okay, so how does this free and fixed mean? Free and fixed means that remember that the variables in the left in this atom that we're cutting here is exactly correspond to z1, z2, z7, z8. Remember, this is z1, z2, z7, z8. The fact that we are cutting this here just represents that we are writing this integral associated with this delta in the first line, and z1, z2, z7, z8, they are exactly listed here. Okay, the fact that they are free means they are listed in the first line. Okay, so now what you have for the rest of molecule, you are having these other variables. We're having this for example, this will be z6, z9, and then you will have z3, z5, and then you have this guy z4. And then now this is also the same as z7, is also the same as z8. Okay, notice that this and this are exactly matches this and this, and in the integral, exactly, since we are dealing with with the iterated integral, when we work on the integral in the second, third lines, then the variables z7 and z8, they are viewed as fixed. Okay, the variables are viewed as fixed. We fix the values of z1, z2, z7, z8. We integrate in the second and third line, and finally we integrate back in z1, z2, z7, z8 to get the first line. So this is how we do the iterated integrals. And this is precisely because these variables are now fixed when we're dealing with the integral in the second, third line. Okay, so this means that this is a diagrammatic representation of this integral kind of reduction that we're doing in this writing here. that exactly corresponds to the process of cutting this atom as free using this definition here. So let's say we can work on do a second time. Then we cut then we can cut another one as free, and this time let's say we cut this as free. Okay, let's say we have this sorry, this fix. This is fixed. This is fixed. Okay, and then we cut. Let's say we cut this as free. How it has free? We turn this into. We turn this into this and this. Okay, and we have another one here. Now you see this should be free. This should be fixed. Again, we're cutting this here, and this green edge is turned into one free and one fixed. And of course, here is also fixed, and then here is fixed. Okay, so if we measure the, if we locate the variables, so see this is Z4, this is Z4, Z6, and this is Z7, Z9, and here this is Z5, Z8, Z3. Yeah, okay, and then so this is Z9, Z5, Z8, Z3, and you have this is Z9, Z6, Z4, Z7. Okay, so in the second integral, so since we are cutting this atom as free, the integral associated with this atom is written in the second line. In the second line, you see we're integrating in the in this factor, and then we're integrating in T2, of course, and Z3, Z9, Z5, and they exactly correspond to Z3, Z5, and Z9, which exactly correspond to the free variables. We'll also exclude the fixed variables. Okay, and finally in the third line, we are only integrating two space variables, Z4 and Z6, and because these are the only free variable that is left in the last atom you have here. Okay, so this is the kind of cutting sequence, definition of cutting, and then how this exactly corresponds to the manipulation of the integral. Okay, so let me summary a little bit. By cutting operations, we can reduce the whole integral, probability m, which is equal to the integral of the product of delta or what, or blah blah blah, to an iterated integral. And at each time, we are integrated in the free variables only, and the fixed variables are viewed as fixed. Okay, so conceptually, what is the advantage of this? It's exactly that we have this whole integral. We're reducing it to iterated integrals, and in each step, in each iterate, we are only iterating in a few kind of we're only iterating in one time variable. We're only iterating in a few space variables, and these integrals can be calculated, can be evaluated, explicitly. And if we can gain, get some upper bound, gain some powers or epsilon from the integral, then we can see from these individual terms. So this kind of you can think of it as kind of localized point of view. Like we break this whole picture into a number of local pictures, and if we can gain at each local picture, or at least if you can isolate some good local pieces, if you can isolate sufficiently many good local pieces, then we can get the sufficiently many power gain in our whole estimate. Okay, so then the goal is to estimate these local integrals. So for example, here you'll see that each line involves exactly one atom, one collision, one time variable, and at least two and at most four space variables. And this one only involves one collision, and this one only involves one collision. Okay, so we estimate these local integrals and identify those that gain powers. Of course, like here we are thinking of each iterated integral involves exactly one collision, one atom, but we can also put two of them together, and we can allow those integrals that involve two collisions and two time variables. And this is, of course, doesn't change the whole thing. And second, need to construct a cutting algorithm that exhibits many objects that gain these powers. Okay, so due to time limit, this first one is just elementary kind of integral calculation. So we'll not talk about that in details due to our time limit, but I will show you what are the kind of so-called good, components and what are so-called the normal components, which are this. So for part one, one atom of degree 3. Here, by the way, so atom is just these atoms, and degree means a number of free edges, which we exclude a number of fixed edges, because the number of fixed edges they don't attend the integration. Yeah, they are fixed variables. So let's say we have this. If we have this fixed, and this is free, this is free, this is free. So this is normal component. And this means that basically this integrating this in this atom just corresponds to having a normal collision. Let's say you have this edge being fixed. We want to find another edge that collides with it and nothing else, and then you just have a normal collision with probability 1. Okay, probability or tau. Okay, so there is no gain. However, there is a case of two atoms each of degree 3. And this is a kind of the main thing that we are extracting. Let's say if we have two atoms like this. Okay, so let's say we have two fixed ends. We call this is fixed. This is fixed. The others are free. Okay, so then you see each each atom is going to have 3 free edges and 1 fixed edges. And what does this mean? This is kind of a good component, which we call the 3-3 component. And here I'm calling just a single 3. And physically, what does this represent? Remember that you have a fixed particle here, staying here. Then we say this particle goes colliding with it, which would have the normal probability 1. But then not only you need this particle collides with this, and then it's going to collide again with another fixed particle. Remember, this also fixed. You see, this is precisely the case we are dealing with in our very first toy model, that we have this particle C here, that not only it collides with B, but after colliding with B, it again needs to collide with A. Okay, and this will give you a positive power in epsilon, because this thing is not going to happen every day. And then the same thing here. This particle, it goes collides with this fixed particle. Let's use different colors. Okay, it goes collides with this fixed particle, fine. But then after this, it's going to collide with another fixed particle here, collides with this, and collides again with this. And this is not going to happen every day. Okay, and this means that this is going to have a small probability, vanishing probability, with gain, the integral. So there's no gain means integral is O1. Here integral is O epsilon to alpha for positive alpha. Okay, so it turns out that these two objects are kind of the major object will be looking at and looking for in our proof. And if once we can get sufficiently many 3 components, then will be good enough to conclude that we have enough power gain. And here, of course, the 3-3 is going to be comparable to the number of recollisions. So then we need to find a cutting algorithm that contains overall many produces these 3-3 this particular good object. Okay, and maybe in the last 10 minutes, let me just briefly describe what the algorithm would be and the intuition. So to explain the intuition of the algorithm, how do we get this many good components? Let us go back to the to this multi-layer picture. So let's copy this again. Okay, so we have this multi-layer picture. And then there is actually a 2-step process. So first step is we're going to reduce the case of multi-layers. So there are total, L layers and in principle, many layers. Reducing the case to the case where we only have 2 layers. So for the algorithm, okay. So first, reduce how to do this. Basically, we do the following. Recall, rho is basically the maximum size of the Sj, where J is the size of cumulant expanded layer J. So it's the SL, the last value is the number of red particles, and next the number of blue particles expand in this cumulant, and number of pink particles, and so on. So we choose the J such that Sj is max. We choose some J at this level. There are kind of sufficiently many particles that cross this cross this time layer. The point is that these particles, they are going to be connected kind of in the layer immediately above. Okay, so these Sj particles are connected in layer, let's say J. Okay, and they are also connected in the backwards layers, J minus 1, J minus 2, 1. Okay, which means that, remember these pink particles, they are going to eventually, they're going to be connected, like this. Yeah, eventually they're all going to be connected kind of across all these layers. But then we can find one single layer such that the most, we have, since we have this little L layers, let's say, we have these finitely many layers, we can choose one single layer where you have the most number of extra connections within this single layer. Okay, so let's say, we have 100, particles along this line. When we go to the next layer, one of them gets connected or two of them gets connected. When you go to the next layer, the three of them gets connected. When you go to the next layer, there are kind of 5 extra connections. And in the end, okay, there will be one layer where there is kind of a sufficiently many, the most number of extra connections. So let's say we go through this layer, we get 20 extra connections, and then we're going to choose that layer. Okay, so then we choose layer with the most number of extra connections. Okay. Call it layer Q. So picture here. So if we draw it like in this way, so we have this J minus 1 tau, let's say this J tau, okay, and we have 0. Okay, the picture here is that we're having this, Sj particles here. So we're having these Sj particles here. So this is Sj, if you want. So this is, okay, so first of all, we know that all these particles, they are connected in these J layer. So they are all connected. So we don't need to worry about them. So they will be connected. They will be kind of mostly kind of connected like this and so on. So you don't need to worry about them. On the other hand, if you consider all these particles, going down to all the bottom layers, let's say we have okay, so let's say at in the next layer only 2 of them gets connected, and we have and then in the next layer only 2 of them gets connected. Okay, but most of them, they still don't get connected until they reach so this is Q minus 1 tau, Q tau. Most of them, they still don't get connected until they reach this layer. Okay, so let's draw it. So let's draw it again. So we have okay, so we know they are connected here, which we don't need to worry about. This is layer L. We go to the next layer and next. 0. This is Q. Okay, so you may have some connections here, but it doesn't matter. The majority of the particles are not connected to each other until they reach this layer Q, where they really gets connected. Then you see, if you only take this layer, the layer L, and this layer Q, and ignore everything else. Whatever happens in the middle, it doesn't matter to you at all, because if you only focus on these two layers, then these two layers is already going to provide you sufficiently many recollisions. Okay, and these particles, remember, they are connected in the top layer. They are again connected in the bottom layer. Okay, and whatever in between, you can simplify this to the picture. Well, you only have two layers. Picture is we have two layers. You're going to have this, this, having this. Okay, so in this way, we are having only this layer Q and layer L, and it's enough to produce enough many recollisions. And if we can reduce the two-layer case, then we can, if we can solve the two-layer case, then we can guarantee the kind of the number of good components. So then we can reduce to two-layer case. Okay, and finally, in the two-layer case, maybe give me like extra maybe if I have still like 5 to 10 minutes, so let me briefly discuss what happens in the two-layer case. It really requires a kind of a complicated technical manipulation of the algorithm, but essentially I can tell you this. So two-layer case, there exists a dichotomy. Let's consider kind of a typical case, which is also kind of simplified case, but it's a typical case, and contains already most of the kind of the most difficult component. So let's say we have two layers, okay, and then we have this in the upper layer we have a tree. So whatever tree we have this, okay, in the bottom layer we have a tree or a forest, and then we have kind of these kind of connections which corresponds to the correspond to the the recollisions and so on. Okay, so imagine we have this picture. So let X be the set of of atoms. Again, here the notion atom means a collision. That on the top layer, remember we have two layers, we call them the top and bottom, that are connected to the bottom layer. And turns out the dichotomy has to do with a number of connected components of X. And let the lambda of X of X. So let's say in this picture, in this picture, what is X? So this guy belongs to X because it connected with something in the bottom. This guy belongs to X, this guy belongs to X, and this guy belongs to X. And then if you look at X as a subgraph, then it's not connected because this is X, this is X, this is X, this is X, and these are not connected because this guy is not in X, not X. Okay, and this means in this case, lambda X is lambda X, the number of components, connected components of X is pretty big. Okay, on the other hand, there is another case. Let's say when we have on the top you have this, on the bottom we have this. Again, they're connected like this. Then you see everything in the top is in X. So everything is in X. And because of this, the set X is actually connected. So number of connected components X is actually very small. It's actually 1. So this dichotomy so if lambda X is bigger than or equal to rho, remember rho is the total number recursion that we're aiming to gain in our algorithm, then we can first cut all the atoms in bottom layer. Okay, and then we cut atom in the top layer to get good components. And the rationale for this is when we cut everything in the bottom layer, then those atoms in X in top layer will become degree 3 because they will have one fixed end, correspond to this thing, being cut. Once this is cut, this will become a fixed end. And being a fixed end, since fixed end doesn't count as a degree, so you have degree 3. And since they are not connected, we're having degree 3 atom being separated by degree 4 atoms. And this is the case where you can gain. Essentially, if you have so this represents degree 3 atom. Okay, and this you can gain because you first cut if you cut this degree 3. And this adjacent atom become degree 3 also. And you can cut this, which is good. Then you get sorry, and the next thing gets to degree 3. Again, this is good. It's also good. Okay, so this is kind of a brief kind of discussion. Of course, in reality, you need to work a lot, really a lot more to make everything a precise algorithm. But this is my idea. And finally, if lambda is number of components is less than rho, then we'll cut keep cutting the top layer. And in the meantime, if any kind of a 3-3 occurs in the bottom layer, and actually for technical reason, we'll include a similar structure called 3-4-3, but this is minor details. We remove it immediately. It turns out that in this way, we can actually get until we apply this kind of dichotomy, this kind of a different algorithm, and we can get enough many good components. So the proof is little bit kind of it's will be kind of too long given our time, but I'll show you one example. If you have this in this picture here, where lambda x is small, if we execute this algorithm, let's say you first let me just draw it here. You first choose this, okay? You cut the top one. We cut it. We cut it. That means we cut it here. Essentially, let's draw it here. Let's say we first cut this one. Okay, and then we cut this one because we keep cutting the the one on top, and now you see we get a 3 3 here in the bottom, so we'll cut it. We'll cut it. And then this way we get a 3 3 here. Remember, this is 3 3, and then we cut it. And then this guy, we get another 3 3 here, and we keep cutting it. And in this way, again, we get sufficiently many components by iterating this process. So let me conclude by saying that the proof is actually 10 times more complicated than this, because in reality, you need to consider, first of all, you are having these complications of so-called overlap nodes, which is a slightly different kind of things, and you need to kind of adapt your definition of cutting even to accommodate all these kind of technical points. And even in the main case, in the reduction case, it's much more complicated than what I'm just saying now. You need to kind of suitably minimize a certain quantity, and you need to do the selection. And before the selection, you even need to do a kind of a so-called refinement process, which we all don't have time to talk about. And even we are in a two-layer case. The dichotomy we are describing here is a key part of proof, but it's again oversimplification. You have to consider the case of the so-called two connection case, which has a big chunk of discussions, and you need to consider the case where you need to do a number of kind of pre-processing, again a bunch of discussions, and here the set X, the definition of set X is not just as simple as this, and you need to rely on not just two algorithms. In reality, you need to rely on almost like let's say 7 to 8 different algorithms, and each of them, some of them will be applied kind of in a certain order, and some of them will be applied in different cases. You apply algorithm 1, and then if something happens, you apply algorithm 2. If something doesn't happen, you apply algorithm 3, and in the end you're having a pretty complicated procedure. But I mean the key idea in the algorithm is basically this dichotomy, which actually comes from a very intuitive thoughts. But okay, so in the end, we are able to to define and execute all these algorithms, in different cases, all these algorithms together, and putting together, they allow us to prove this estimate, this combinatorial estimate of the number of 3 components, and then this combined with our earlier estimate on this iterated integrals leads to the desired estimate of these interaction diagrams. And then finally, this allows us to complete this estimate of the cumulants, and then we conclude that we have proved this general long-time derivation result. So, well, okay, there is also this iteration process of defining the approximate solution to Boltzmann. There is also a truncation error, which should follow from kind of similar arguments, but with a little bit more, slightly more inputs that we are not talking about. Okay, so this is this is it, and we'll